In this video, we are going to have an insight, an understanding of why would a transistor, a bipolar junction transistor, moves from being active to saturation, and what are the determining factors, what are the factors that make the transistor move from the active region to the saturation region. We'll see in this video that the determining factors, the important factors that affect the movement of the transistor from active region to saturation region is the base current and the resistors in the collector emitter loop. So this is called the collector emitter loop, the loop that starts from the supply connected to the collector and then you go to the collector emitter ground. So this is called the collector emitter loop. The resistors or the resistances in this loop also is an important factor that determines whether the transistor operates in the active region or in the saturation region. In order to understand or to see by examples how a transistor moves between these two regions, let's assume for the coming examples, for all the coming examples, that beta equals 100 and VCE saturation equals 0. So when a transistor enters the saturation region, VCE saturation or VCE will be 0 volt. Let's start with the first example. So let's assume that we have a bipolar junction transistor with the RC, the resistor connected to the collector is 1 kilo ohm, VCC 10 volt, and the base current is 0.01 milliampere. And let's assume that this transistor is active, and let's calculate IC. So if the transistor is active, then IC will be equal to beta I base, which is 100 multiplied by 0.01 milliampere. So this will give you 1 milliampere. Once we calculated IC, we can calculate VCE. So VCE will be 10 minus the drop across this resistor. So 10 minus IC RC, and IC is 1 milliampere multiplied by 1 kilo ohm. So this will give you 9 volt. And 9 volt is bigger than VCE saturation, right? It's larger than VCE saturation. So we can say here that our assumption of active region is correct. So this is our main circuit. We assumed active and we checked and our assumption was correct. Now let's move to the next circuit. What happens if we increase the base current from 0.01 milliampere to 0.1 milliampere? Let's see what happens. Let's again assume active. Assume active. Once we assumed active, we can calculate IC. So IC equals beta I base. It will be 100 multiplied by 0.1. So IC will be 10 milliampere here. So instead of 1 milliampere, IC will increase to 10 milliampere. And then we can again calculate VCE. VCE will be 10 volt minus the drop across the resistor minus IC RC. But IC here is 10 milliampere. So 10 milliampere multiplied by RC, which is 1 kilo ohm. This will give you 10 volt. So VCE will be 10 minus 10. It will be 0 volt, which is exactly equal to VCE saturation. So here we notice that the transistor moved from being active. When we increased the base current from 0.01 milliampere to 0.1 milliampere, the transistor moved from being active to a point that we call edge of saturation. Edge of saturation means it's the point exactly at the edge between active and saturation. This is the point exactly at the edge between active and saturation. So we say that the transistor now is at the edge of saturation. And by the way, this point at the edge of saturation, it can be considered, still can be considered as active and can be considered as saturation. It's a critical point in between the two regions, okay, the edge of saturation. So still our assumption can be considered here to be correct. There is no problem because this edge of saturation can be considered both active and saturation. But the point here is what happens if we increase I base anymore? So if we try to increase I base more than that, for example, if we increase I base to 0.11 milliampere, let's see what happens. and this is 1 kilo ohm. This is RC equals 1 kilo ohm. This is 10 volt. In this case, if we assume active, we will find that IC equals beta I base. It will be 11 milliampere. In this case, since IC is 11 milliampere, VCE, if we calculate VCE as 10 volt minus the drop here, minus IC RC, it will be negative 1 volt. So we ask ourselves a question here. Is it possible that the transistor is active and VCE is negative 1 volt? VCE is less than VCE saturation? Of course not. Of course not. Because in order for the transistor to be active, VCE must be greater than or equal to VCE saturation. Here we assumed active, but we found that VCE is less than VCE saturation. Then we say that our assumption is wrong and the transistor is not active anymore and it will enter the saturation region. So let's ask here, what happened? What happened? Why the transistor entered the saturation region? Let's see from the beginning. In the beginning, when we increased I base from 0.01 to 0.1, IC increased and it kept track of the value beta I base. So IC, it was beta I base here. When we increased I base, IC also stayed as beta I base, increased with it and stayed as beta I base. And VCE reached 0, the value of 0 volt. So VCE reached 0, which means that the 10 volt here, all of it became a drop across this resistor. So if we consider this loop, the collector emitter loop, VCE became 0. This means that the drop across this resistor became exactly 10 volt. Now, if we try to increase I base anymore, will IC increase? No, IC will not be able to increase anymore. Why? Because the drop across this resistor cannot exceed the supply voltage that you have. You have a supply voltage of 10 volt. Here, at this point, IC RC reached exactly 10 volt and VCE reached 0, right? If you try to increase I base anymore, IC will not be able to increase because in order for IC to increase, the drop across this resistor must increase. And the drop across this resistor cannot exceed 10 volt, so IC will not be able to increase. IC will stay at its value. It will stay as 10 milliampere. Even if you increase I base, then IC will stay here as 10 milliampere and the transistor will enter the saturation region. In this case, if you increase I base and IC stays, then IC became what? IC became less than beta I base, right? So if you increase I base, but IC doesn't increase with it, it will stay as it is, okay? Then IC will become less than beta I base and the transistor enters the saturation region. So here, when you try to increase I base in the beginning, you increase I base, IC increases. You increase I base, IC increases until you reach to a point where VCE reaches 0 and the drop across the resistor here is equal to the supply voltage. At this point, IC will say, no, I cannot increase anymore. If you increase I base, IC will not increase, and hence, this is the point at which IC will be less than beta I base, and the transistor enters the saturation region. So the first reason that you enter, or that the transistor enters the saturation region, is increasing I base. If you keep increasing I base in the beginning, the transistor will stay in the active region until you reach to a point where VCE reaches 0. The drop across the resistor here is equal to 10 volt or equal to VCC. At this point, IC will not be able to increase anymore, and this is the point at which the transistor enters the saturation region. The second reason that the transistor enters the saturation region is because of the resistances in the collector emitter loop. And here in the collector emitter loop, we have in our example, we have the only resistance in the collector emitter loop is RC. So let's try to increase RC. If we increase RC, for example, if we use 10 kilo ohm instead of 1 kilo ohm, and let's go back to the original circuit. This is the original circuit. We have 1 kilo ohm and I base 0.01. We'll fix I base and we'll increase RC to 10 kilo ohm. So I base is the same. We'll fix I base to be the same. We'll not increase I base. So here the transistor was active, right? Now we are using the same I base, but we are going to increase RC to 10 kilo ohm. And we have VCC here is 10 volt, and this is VC. Again, we'll say assume active. We'll calculate IC. So because we assumed active, IC equals beta I base, which will be 100 multiplied by 0.01. It will be 1 milliampere. And now we can calculate VCE to be 10 volt minus the drop minus IC RC. IC is 1 milliampere and RC is 10. Then it will be 10 minus 10. It will give you 0 volt. So here VCE reached VCE saturation. So we say that the transistor moved from being active to the edge of saturation. So it was active here. When you increase the value of RC from 1 kilo ohm to 10 kilo ohm, VCE became VCE saturation, equal to VCE saturation, which means that the transistor is now exactly at the edge of saturation, at the point between active and saturation, the point that we call edge of saturation. Until now it's fine, but what happens if we increase RC more than that? If we increase RC more than that, okay, for example, let's use 11 kilo ohm, then for RC equals 11 kilo ohm, then VCE will be assuming active, then assuming active, assume active, you will get the same IC, of course, the same IC 1 milliampere, and VCE will be 10 minus IC RC, which will be in this case, IC RC in this case will be 11. So it will be 10 minus 11, which is negative 1. And it's impossible for the transistor to be active while VCE is negative 1. VCE negative and less than, of course, VCE saturation. Right? Why is it impossible? Because in order for the transistor to be active, VCE must be greater than VCE saturation. What else? That the drop here now, the drop across the resistance now, it's ICRC, which is 1 milliampere multiplied by 11, it's 11 volt. It's impossible that the drop across the resistance be higher than the supply voltage, right? The supply voltage is 10, so it's impossible that you will get a drop across the resistor in the loop more than 10 volt. So your assumption of being active is again wrong. So again, what happened here? What happened here? Again, when you increased RC from 1 kilo ohm to 10 kilo ohm, the transistor stayed in the active mode. It stayed in the active region. But IC stayed as beta I base, 1 milliampere, no problem. And the transistor is in the active and the IC equals beta I base. But when you tried to increase RC more than 10 kilo ohm, then IC said, I cannot stay as beta I base. I have to drop my value. I have to drop my value so that the drop across this resistor is 10 volt. So the drop across this resistor cannot exceed 10 volt. Okay? When the resistor was 10 kilo ohm, the drop across the resistor was exactly 10 volt and VCE was 0. This is the case that we did here. VCE was 0 and the drop across the resistor was exactly 10 volt. Now when you increase RC to the 11 kilo ohm, then what happens is the collector current is going to drop. It's going to decrease to make the drop across the resistor here exactly 10 volt. So as you increase RC, the IC after this point, as you increase RC, IC is going to decrease so that the drop across the resistor will be exactly 10 volt. So once you reach the edge of saturation, if you increase RC more than that, then the current IC is going to drop value. It's going to decrease its value so that the total drop across this resistor is 10 volt. It cannot exceed 10 volts. So IC is going to decrease so that the multiplication between IC and the resistance is exactly 10 volt. In this case, if IC decreases while I base is fixed, so IC decreases while I base is fixed, then IC will be less than beta I base, and we say that the transistor entered the saturation region. So we discussed here in this video the main reasons that the transistor moves from being active to saturation. The first reason is when you increase I base, in the beginning the transistor will stay active until you reach to a point where the drop across this resistor is exactly equal to the supply voltage. After this point, IC will say, I cannot increase anymore, I will stop increasing. So you increase I base, but IC doesn't increase, which means that IC will be less than beta I base. In the second case, you fix I base and you increase the resistance. Whether this resistance, or if you have a resistance in the emitter, this is also considered to be a resistance in the collector emitter loop. When you increase the resistance here of the collector, okay, in the beginning the transistor will stay in active region, but once the drop across this resistance reaches the value of VCC, reaches 10 volt in our example here, then IC will say this is my end. I cannot stay like this anymore. So if you increase RC more, IC has to drop so that the drop across this resistance is equal to 10 volt. If you increase the resistance, IC has to decrease. And if IC decreases while you fix I base, then IC will become less than beta I base, which means that you enter the saturation region. That was just an insight of an understanding of how the transistor moves from being active to saturation. See you in the next video, inshallah.